All right, standard deviation is what we're going to look at next when it comes to analyzing data. What is your standard deviation? Basically, when we're dealing with standard deviation, what we're asking, the question we're looking at is, given my average, and here's my data points again. Remember, I'm trying to figure out how much, if I were to sell the trees here on my property, sell some of the trees, what kind of money could I expect? All right, so, but I need to understand what trees I have, their sizes. So I measured, randomly chose 20 pine trees, and I measured their circumferences in centimeters, and these were the circumferences that I got. Okay, so in the last section, we looked at mean, median, and mode, and how to use those tools for looking at data and trying to analyze and understand our data. In this video, what we're going to be looking at is the standard deviation. We need one piece of information, and that is the mean. We need the average. So we already calculated that at 71.05 centimeters. That's my average for these data points. Okay? We call that average, when we're doing statistics, we call that average bar X. Our data points are just X. The number of data points that we have is called our N value. That's the number of experiments we've run, the number of trees we've measured, the number of frogs we've caught, the number of milk we buy, whatever. That's our N value. The bigger the N value, typically the more accurate is our number. We looked at that, remember when we talked about probabilities. In probabilities, the more we roll the dice, the more we flip the coin, the more our numbers begin to stabilize. Flipping a coin at 50%, right? So our 71.05 is our bar X, and that is our average, our mean. What we're looking at when we're looking at standard deviation is we're asking ourselves this question. Since we know that this is the range right here from 17 centimeters to 131 centimeters for the circumference of my trees, our average is 71.05 centimeters. The question I'm asking now is, how far on average do my trees range from the average? Let me say that again. How far from average do most of my trees lie? We'll talk about how to look at a distribution curve in the next video. And what we'll see is that within that first standard deviation, what we're about to calculate, what we'll find is there's about 68% of my data set is going to be within that range, assuming that it's a normal type of a curve. And we'll talk about that later. So that's what I'm asking. At what distance, how far from 71.05 are most of my trees? That's the question I'm trying to ask. Okay, where are my trees clumped at? Okay, so to do that, we have to do a couple of different things. All right, so we have our data set that the raw data we went and measured. We then took the average that gave us our bar X. The first thing we need to do is we need to subtract the average from each of our data points. So we have to subtract 71.05 from 17, and then 71.05 from 18, and then from 23, and then from 31, etc., etc., etc. Okay, so this step, if you see how I've kind of drawn out this data table, there's our X, here's our bar X. This next one is X minus bar X. And that's the data set that we're going to put here. So I've written up the numbers. I've got them all down here. You can see that a lot of these are negative. That should make sense. We've got 17, 18, 23, 31. They're all subtracting 71.05. That's giving us negative numbers. Here's the problem. If we add up these negative numbers, since we're looking at averages, if we add up the negative numbers and add up the positive numbers, pretty much it gives us 0. Well, 0 doesn't tell us anything. It just brings us back to the average. Remember, we're looking for how far from the average is the normal tree, or an average tree, or some random tree. How far off of the average can I expect that tree to be? Most of my trees on my property. Well, this, if I just use that to analyze, we would see that everything is pretty much average, everything. So that's not going to help us. We have to get rid of the negative numbers. Now, the way that we're going to do that is the next step. The next step is we take bar minus our x minus our bar x, which are these numbers, and we simply square all of those. Hold on, and I'll show you what that looks like. Whew, them a lot of big numbers. So notice that as I square these, negative times the negative gives us a positive number. So what that does is that makes all of my numbers now positive. Okay, gets rid of the negatives, which is what I want. Because I'm working with distances, think about it for a second. It's impossible to have a negative distance. I'm looking at a graph and I'm asking how far from the average, from the mean, how far are most of my trees? How far is a distance measurement? You can't have a negative distance. I don't care if you're in your car driving backwards, you're still going positive mileage. You're still putting on positive miles. Unless you get a car from the 1950s where the odometer works the other way around, you'll have to look that one up, but it actually happens. You can drive, never mind, I'm getting distracted, look at me. So we have all of those numbers up here now. We've squared all these terms. Okay, the next thing we have to do is we have to take the sum of our x minus bar x squared. We have to sum all of those numbers together, okay? That Greek letter sigma, that means sum. When you see that funky little triangle E looking thing, that means sum of. We're going to take all these data points, we're going to add them up. I have the number right here. It is 23,647.9. That is my number, all right? That is the sum of all of these numbers added up. Now, in a sense, what I'm doing now is I'm going to take the average of my averages. The difference is I take the next step in this is I'm going to divide this number, the sum of my x minus bar x squared, I'm going to divide that number by the number of data points minus 1. Not going to get into why it's minus 1, just know that it does work that way, okay? You can look up the theory on that. Some people will divide their number by n. Most individuals divide it by n minus 1. So I have to divide this number by 19 since I have 20 data points. Okay, so dividing that by 19, I get the number 1,244.63. That is the sum of my x minus bar x squared divided by n minus 1. And then the last step I want to do is, remember I squared all these terms? That overinflated my number. Remember, I'm looking for the average distance. What is the average circumference of my trees? Where are most of my trees? Their circumferences, how far are they from the average, okay? I'm not going to have trees. If my average is 71.05 and my largest tree is 131 centimeters and my smallest tree is 17 centimeters, I cannot have a tree on average that is 1,244 centimeters. That doesn't make sense. So because I squared my terms here, I have to get rid of that square. So the final step in doing a standard deviation is I'm going to take the square root of the sum of my x minus bar x squared minus n, or divided by n minus 1. So that 1,244.63, I'm going to take the square root of that to get rid of this math here, and that gives me a number 35.28. That, my friends, is the standard deviation of these numbers. So as I measured out my trees, again, what am I asking for? I'm looking for how far, where are most of my trees clustered? If the average size of my trees, given my random data set, if the average circumference of my trees is 71 centimeters, how far from that range, give or plus or minus, how far are we? How far are most of my trees from that number? And they're just over 35 centimeters from that number. And that's what standard deviation is. It's a powerful, powerful tool, because this then helps us to understand where our data is clumped. And that's what's important. I should have said where our data are clumped. Data is plural. Isn't that weird? So this is how you calculate your standard deviation.